So, we were discussing central force motion of a particle under a central force, and I defined a central force by saying that there is a particle which is moving under a force, and then there is a point, so that all the time the force is along the line joining that point and the particle, and the magnitude only depends on the distance from that particle. So, if you have x y z axis, x axis, y axis, z axis, and then you have a particle here, and at some time t it is here, this is the radial line OP, and suppose it has a velocity in some direction, it has a velocity in this direction, right. The choice of x y axis can be made after I know the velocity of this particle. At this particular instant it will have some velocity. So, there will be a velocity vector, and then you have this OP. So, you choose your x y axis in the plane of this OP and this V, so that you have at least initially the particle is moving in this plane, and then the z axis is perpendicular. And if the force on the resultant force on this particle is like V Fr r cap, force is equal to Fr r cap, r is this distance and r cap is unit vector in this direction, this is r cap. Okay, it can be away from O or it can be towards O, that will depend on this function. This function can be negative, this function can be positive. So, the force can be away, force can be towards. So, those things will be taken care of by this scalar function small f r, but the direction is along OP, and the magnitude of the force depends only on this distance, then it is called a central force. And then we saw that the torque is 0, torque on the particle is 0, because at any time, what is torque? Torque is r cross f, and since f is in this radial direction, r vector is in the radial direction. So, this is 0, and torque 0 means the L vector is constant, because your torque is dl dt, right. And if L vector is constant, and then L vector is m times r cross v, and L is perpendicular to this r vector and also perpendicular to this v vector, and initially, at least initially, r is here, v is here. So, r cross v is in z direction. So, this is sum L naught times k cap. So, initially there is no velocity component in z direction, and velocity has to remain perpendicular to the z direction, and therefore, you cannot have the particle out of this xy plane. And so, from here itself we can say that the path of the particle under a central force is in one single plane, whatever be that plane. It is a two-dimensional motion, it is not three-dimensional motion, although it is free to go anywhere as such, no boundary is there. It is not constrained somewhere by putting some sheet or something that you cannot go away from this, but still it will go in one particular plane, and the plane will be decided by how the motion is started, right. So, if you have the center of force, the force is away from this center or towards that center, and then you have velocity that decides the plane, and once it is in that plane, it will always remain in that plane, coplanar. Then the other thing we found is that the magnitude of L is m r square theta dot, okay. this angle is known as theta and this distance is known as r. So, r square and theta dot means d theta dt, m r square d theta dt. This is the magnitude, and since L is constant, right, since L is constant, this magnitude is also constant. And from this fact that the magnitude is constant, we can derive another nice property of this central force motion. The path is in one single plane, and now we are going to derive yet another beautiful property under central force motion, and that is, if the particle at time t is somewhere here, this is x axis, this is y axis, this is r, this is theta, and in dt time, this is at time t, and in dt time it reaches somewhere here, and this time the velocity is v. So, this distance is v dt, and this angle is theta. This distance from here to the new position is r plus dr, and the new angle is theta plus d theta. So, this angle is d theta. So, let us first calculate what is the area of this triangle. What is the area of this triangle? Remember, we are talking of infinitesimal time dt, and therefore, this dr is infinitesimally small, this d theta is infinitesimally small, and this whole area is infinitesimally small. What is that area? Let us calculate. So, if I drop a perpendicular from here and call this as h, remember this v dt is this line is v dt. Area of this triangle is half into base into height, half into base into height, and that is half into base is this is the base, one side on which you drop the perpendicular from the third vertex. So, this is base. So, this r, base is r, and height is this one, and this height you can write from this right angle triangle, this height will be r plus dr sine of d theta, r plus dr sine of d theta, right. This is height, and we have dropped perpendicular to get that height, and then this is a right angle triangle, this is the hypotenuse, r plus dr is the hypotenuse, and this is the side h opposite to angle d theta. So, sine d theta will be this h divided by r plus dr, and h will be r plus dr into sine d theta. But since the angle is infinitesimally small, sine d theta is same as d theta in the limit. So, this will be half into r and into this r plus dr and then d theta, and that is half r into d theta is r square d theta, and then plus r into dr into d theta. And since we have first order infinitesimally small quantity present here, and this is that second order infinitesimally small quantity, there are two infinitesimal quantities dr and d theta is product of that. So, this can always be dropped in presence of this. This is not an approximation. This is not an approximation because we are going to take limits. We always talk in terms of the limits. Final results in calculus are the limits, and there it is exactly the same. So, this can be dropped out, and this area dA is equal to half r square and then d theta. That is the area, and this is the area swept by this radius vector in time dt. This was the radius vector. This was the radius vector, and then this radius vector is, suppose this is going, this whole radius vector, actually the particle is going, but you draw this radius vector from each point of this path. So, as if this is sweeping this area, this radial line is sweeping this area in time dt. So, the rate at which this area is being swept, this radius vector is sweeping the area, will be dA dt, and that dA dt will be half r square d theta dt, that is half r square theta dot, and that is L divided by 2m. Constant, independent of time. The magnitude of angular momentum does not change with time. L is a constant. L by 2m is a constant. So, whatever be the form of central force, whatever be the functional form of that f small f r, this function here, for all central motions this is true. The radius vector sweeps equal area in equal time, because the rate at which this area is swept is constant. Radius vector, what is radius vector? I do not know where is the radius, there is no circle out. Okay. It can be a circle, but in general it can be anything else. So, the radius vector origin to the particle, that vector is known, the position vector is known as, also known as radius vector. The radius vector of the particle sweeps equal area in equal time. Familiar statement? It may be sounding very familiar, somewhere you have heard it. Yes, you have heard it when you are studying Kepler's laws. This is the second Kepler's law, second law of Kepler. And from in what context these laws were given? Planetary motion, motion of planets around the sun. So, there are some 8 planets or 9 planets at the time of Kepler, perhaps there were 9 planets. So, different planets are going in different elliptical orbits around the sun, with sun at one of the foci. So, that is Kepler's first law. The second law is the radius vector from the sun to the planet sweeps equal area in equal time, and the third law is about the time period. Square of the time period is proportional to the cube of the semi major axis of the ellipse. The second law of Kepler is valid for all varieties of central force motion, whatever is Fr. Now, specifically if you talk of that sun planet type system, you know the force is given by G m by r square, magnitude, and then the direction. So, we can write minus and r cap here. So, this is taking sun as the origin and planet as the particle. So, if this is the origin, then this distance is r, this is r cap vector, it is attractive force. So, it is this. What we are doing is very idealized case. Here the sun will also get attracted towards the planet, and therefore, sun will also have some kind of central force motion like that. So, in our case the origin fixed, the center of the force is fixed, although sun is very heavy as compared to the planet. So, the mistake is not large, But then you can reformulate this sun planet system, neglecting the effect of other planets, of course, asteroids and so many moons and all those things are there. Forget that. If you have just one center here sun, another center say earth, then although the sun is also moving, the earth is also moving under mutual attraction, but that problem can be reformulated to match with this description. So, essentially what we have is our Fr here, this Fr, this f of small r is of this type. Fr is minus some constant divided by r square, minus some constant divided by r square. This is known as inverse square law. So, if Fr is of this variety, you are considering a particle on which this central force is acting and the magnitude of central force is given by this 1 by r square type, and it is always directed towards that origin, then it will very close to our planetary system or very close to the Bohr's model hydrogen atom, where proton is sitting at the center, electron is going around it, and very close to that Rutherford scattering, where you have a nucleus, alpha particle is sent, and because of that force, of course repulsive force, or if you send beta particles, then it is attractive force. Very close to this situation, the force is 1 by r square type, inverse square type. Now, if this is the case, we can do something more using energy diagrams. Okay. So, let me do that. So, energy diagrams I had talked when I was talking of particle moving in one straight line. I took an example of spring force Vx is equal to half kx square, and if I plot this Vx as a function of x, it is a parabola, and from the shape itself I can tell many things. If this is given and if the total energy is known, then I know what are the turning points, what are the amplitudes, and then as a function of x, how much is the potential energy, how much is the kinetic energy at each time. Many things I can derive from these kind of diagrams. But if the motion is not confined to one straight line, but it can go in a plane in different directions, then how do I plot this? So, it so happens that in this kind of central force motion, we can have a similar thing, energy diagram, but not exactly of this kind that I am just plotting this potential energy as a function of time, because here if this is force, force is equal to minus k by r square r cap, then this potential V of r will be minus k by r, right. So, I just plot this V by r versus r, it will be a hyperbola, and it will also give you some results, but not very useful. So, we do some mathematical manipulations. Let us see what. First is, we write this total energy U, which is half mv square and plus potential energy, which is minus k by r, right. Kinetic energy plus potential energy is the total mechanical energy. This is what I want to use in this diagram, and this V I write as r dot r cap and plus r theta cap, r theta dot and then theta cap. This is velocity vector. I had derived it in the previous lecture. If you look at it, the velocity vector V is given by this, and it is the magnitude of this whole square, that is here V square. So, this is V and then square and minus k by r. Okay, we derived this. We said that r vector is r cap, and therefore, the velocity vector is d dt of r vector, and from there we said it is d dt of r cap, and then we opened it, right, this r d dt of r, which is r dot and then r cap plus r and then d dt of this this quantity, and we saw that this quantity turned out to be theta dot and theta cap. So, r theta dot theta cap, we derived that. Okay. Now, what is that magnitude square? This magnitude square is half m this component square plus this component square. They are components in perpendicular directions. R cap direction and theta cap direction are perpendicular directions, unit vectors in perpendicular directions, and therefore, you have broken the velocity vector into perpendicular components, one along r cap, another along a theta cap, and so the magnitude square is the square of the two components, sum of the squares of the two components. So, this will be r dot square and plus r square and theta dot square. So, this will be the magnitude and minus k by r. And you also know that m r square theta dot is L. So, theta dot is L by m r square. Okay, theta dot is L divided by m r square. Put it here. So, you have half m r dot square, that is first term, and then you have half and m here, r square here, and then theta dot square. So, L square here and m square and r 4 here, and minus k by r. So, this is half m r dot square and plus 1 m cancels with this power, this r square will make it r square in the denominator. So, you have L square divided by 2 m r square, 2 m r square, and then minus k by r. This is it. This is it. So, the total energy U is equal to half m r dot square and then plus L square by 2 m r square and minus k by r. This you can do with any central force, not necessarily inverse square, only this term will be different. If you change the force law, if it is not inverse square attractive force is something else, then this will be something else, and only change will come here, this part will still remain the same. Now, it resembles, now I have only one variable r, not x and y. So, it resembles that motion in one straight line. There we had for motion in one straight line, we had u is equal to half m x dot square dx dt and then Vr plus potential V x y z. This is a function of x. No, it is a one straight line motion. So, the position is just V at x. So, you have half m x dot square and then a function of x, and then we said that okay, we plot this V x as a function of x and then we derive information from here. Now, this equation is somewhat of this type, half m x dot square, half m r dot square, and the same x is appearing here, it is some function of x, and this is some function of r, r dot here and some function of r here, x dot here and some function of x here, right. So, you can draw a diagram where this quantity is plotted, right. Here we plotted this Vx, here we plotted this Vx and derived the equations. Here we plot this quantity which we call V effective as a function of r, and from this we can derive several information about the inverse square, attractive inverse square motion of a particle. Okay, so how do I plot this? The actual plot will depend the actual value of this L, M and K, but we can still have some information about the shape. Say there are two terms here, one is proportional to 1 by r square, another is proportional to 1 by r. If r is very small, much smaller than 1, then what will happen? 1 by r tends towards infinity, 1 by r becomes very large, and if 1 by r becomes very large, 1 by r into 1 by r will again be very large. So, this 1 by r square will dominate over this 1 by r term. Here you have 1 by r, here you have 1 by r square. So, L square, M, K, they are all fixed. So, if you go sufficiently towards that smaller values, if r is sufficiently small, you can always make this much larger than this. So, for very small values of r, this term will dominate, the positive term will dominate, the negative term will be much smaller in magnitude as compared to this. So, for very small r, this value will be somewhere here, and then it will come down, and at some value, which value? L square by 2 m r square is equal to k by r. So, r is equal to L square by 2 m k. At this value, this whole quantity is 0. So, it will cross this r axis somewhere here, it will cross at this position, it will cross. Now, this will start dominating, these two terms are now equal, and after that 1 by r is becoming smaller, as r is going bigger, 1 by r is becoming smaller, and if 1 by r is small, 1 by r into 1 by r is still small, much smaller, and therefore, this will keep dominating. And how is this minus 1 by r? So, if you see minus 1 by r is something like this, and this will dominate 1 by L square by 2 m r square. If I plot, it will be of this type, going to 0. Ultimately, both of the terms are going to 0. Minus k by r will be of this type. So, here they are equal. It will be going like this. This will be falling much faster. Okay. And here they are equal, and therefore, it will come like this. After this, this will dominate, and this will become smaller and smaller. So, it will be of this type. This will be of this type. So, this whole quantity, if you plot, this will be of this type, right. So, now I can remove these dotted ones, I can remove these ones. This is my V effective, and from this diagram, from this shape, we can derive certain information about this inverse square attractive central force motion that we will do next time.